So this presentation is about using the sample mean to estimate the population mean. It's assuming that we already know the population standard deviation, sigma. So somehow we know sigma, but not mu. We'll do that for simplicity at first, and later we'll figure out how to do the more realistic example where we do not know the sigma. But the problem is we want to estimate the mean of a variable x in a really large population, like the mean time required for cells to divide into new cells. And we can't time every individual cell in the population because there's billions of them. So we can't exactly find out the average. And that's a problem. But the idea is to get a simple random sample and find the sample mean. And then mathematically address these questions. Is the sample mean probably close to the population mean? How close is it likely to be? And is it likely to be closer if we can get a really big sample? Okay. And so the example we're going to work with is about cell division, and we're going to suppose that somehow we know that the sample mean, or the population mean time required for a cell to divide is 2.0 minutes. That's not a realistic assumption. If we don't know the mean, we're not going to know the standard deviation either. After all, the mean appears in the formula for the standard deviation, right? So, but even though this is not a realistic example, it's the right place to start for teaching because it simplifies the problem. And so we're thinking, well, we'll have some hypothesis about the standard deviation. We'll say, well, it's probably about 2 minutes. And say, okay, if that's our hypothesis for what the standard deviation is, let's go with that. And then we can figure out the mean. So what we're going to do is get a simple random sample. Let's say that we get 36 cells, and we find out that the sample mean was 31 minutes. That's just for this one particular sample. Okay, so how likely is that to be close to the population mean?
So our job is to calculate a number E called the margin of error, so that 95% of all possible samples produce a sample mean that differs from the population mean by less than E. That's a long sentence, but E is this distance, some wiggle room. And we think that the distance between whatever you get from a sample and the truth, that distance is probably less than E. We want to calculate E. We want to make it so that 95% of the time the sample mean will be not more than distance E away from the true mean. Okay. So in other words, 95% of all possible samples will produce a sample mean. It's between mu minus E and mu plus E. And we can do that. It's actually very easy now because we have the central limit theorem. So the central limit theorem says first that all the different possible sample means, the different x bar 36s that you might get, all those sample means have a distribution, but the center of it is at the population mean mu. The center, the mean of all the sample means, is the same as the mean of the original variable. And the standard deviation of the sample means can be made small because you divide by the square root of the sample size. So here our sample size is 36. So the standard deviation of this curve is the original, the sigma, which we were in the statement of the problem. We said that we're going to take that to be 2 minutes. And then we're dividing by 6, which is the square root of 36. So we get 2 minutes over 6, or 1/3 of a minute, 20 seconds. That's our standard deviation. And so along the curve here, along the x-bar axis, we're looking at the length, the time that you might get for your sample mean in minutes. One standard deviation distance along that line is 20 seconds, or 1/3 of a minute. And so just looking at the curve, you can see that a lot of the area, a lot of the probability under here is in the middle. So underneath a normal distribution curve, 95% of all the area or probability is not more than about 2 standard deviations away from the mean. It's almost 2. It's really, for this calculation, will be a little more precise. It's 1.96 standard deviations. So the margin of error is a distance of 1.96 STDs along the horizontal axis. The distance between the true population mean mu in the middle and whatever you might get from your sample is 95. For 95% of all samples, that will be less than a distance e, which is 2 standard deviations, roughly 1.96 standard deviations along the x-bar axis. Now, all we have to do in the next slide is say, well, how much is 1.96 standard deviations? I mean, and it's already, we've said each standard deviation is about 1/3 of a minute, or 20 seconds. So 2 of those is 40 seconds, so roughly. And so whatever you get from your sample mean, you can be 95% confident that it differs from the truth by less than roughly 40 seconds. Okay. So here's just saying all that in writing. 95% of all samples fall not more than 1.96 STDs away from the truth. Each STD, how big is that? We found it by doing sigma over root n. We got 1/3 of a minute. So you just multiply 1.96 STDs times 1/3 of a minute for each one. That gets you the margin of error in minutes. That's about 0.653 minutes, or that's roughly like 40 seconds. And so in general, here's our margin of error. It was z star times sigma over root n. What's z star? In this problem, the z star was 1.96. But that came from the 95%. If you had a different percentage, you'd get a different z star. You can use Excel. If you're trying to find the edge of the middle 99%, you could use z star you could use Excel to find the z star for that. Okay, and so in this class, the confidence levels we'll just use 99 or 95 or 90%. But when you find the area to the left of z star from a picture, based on the confidence level. So you find the area to the left, and then you put that into Excel, into the norm.inv function to find that critical value of z. And that's it.